started, an AVL tree. So we introduced this concept of like an AVL tree, which was sort of like an improved version of a binary search tree. So if you remember a binary search tree, this is an example here. A binary search tree, it's a tree with every node having two children. Those children can be null. You can see the 7 node has like a null child for its left and a non-null child for its right. Every node has 2 children, which makes it binary. And then it's a search tree, which means that from any node, we have this invariant that all nodes to the left contain a smaller value than a given node, and all nodes to the right contain a larger value than a given node. So you can see this 10, everything to the left is less than it, and everything to the right is greater than it. And this property holds for every single one of these nodes. You can go through and take a look at that. But we do have a problem with just a normal BST, and this has kind of motivated the concept for an AVL tree. So a BST, right, the only invariant that we have is just that all nodes to the left are less than a node, and all nodes to the right are greater than a node. But it doesn't say anything about like the balance of the structure. So you can think of like this, for example. These sequences of inserts result in this BST. And this is a valid BST. It satisfies our BST invariant. But if we did any operations on this, like we kind of introduced the idea that like, when you have a tree, you get this like nice logarithmic runtime because, as the levels grow, like the height of the tree is like logarithmic with respect to like the number of nodes in the tree, usually. Unless you have like a really bad case like this. So we can get this like worst case behavior, which kind of motivated like maybe you want like to avoid this worst case behavior basically. Because if you ask any question about like a BST, like what's the worst case runtime of X in a BST, you'll always want to be thinking about like this type of structure because BST can be this type of structure. So you actually get like pretty bad runtimes for a few, like pretty bad worst case runtimes, which is where this AVL tree comes in. And for an AVL tree, it's just a BST, but it's balanced. So what that means is, we'll kind of define like the concept of balanced. What it means for this class is that the difference in heights between the 2 subtrees of any node is no greater than 1. Kind of a mouthful, but what you can sort of think of as balanced is like this. If you had 3 nodes, this is balanced, right? Because like everything's like there's no like worst case behavior here. We can go back to this definition though. When the difference in height between the subtrees is no greater than 1. I looked at this 8, and I was wondering, okay, what's the height of its left subtree? That's going to be 1. What's the height of its right subtree? That's going to be 1 as well. So the difference in height between these subtrees is no greater than 1, right? Because the difference is 0. By the way, just recalling, like the way that we calculate height is by just counting the number of these like arrows here is kind of how you can think of that. So if we go over here and we look at this tree and we're wondering, is this balanced? Well, the height of its left subtree starting at 10, the height of that left subtree is 0, right? There's no nodes there. There's no arrows. The height of its right subtree is 1, 2. So we can think about like, does this satisfy the property that the difference in height between the subtrees is no greater than 1? Well, the height of the left subtree is 0. The height of the right subtree is 2, so the height difference is greater than 1, so this is not balanced. But similarly, we have these 2 structures are balanced, right? So, even though there is a difference of 1 in the height of the subtrees with this 8 here, we still consider that balanced. And we also consider this balanced, like, 0 and 0, that's also balanced. And yeah, the big point about being balanced is a balanced tree with like n items has a height of O of log n. That's in comparison to like this over here, where a BST, if it's not balanced, the height is going to be O of n for n elements in this worst case. But if it's balanced, it's guaranteed to be log n.